Hello, and welcome to my ICSME research presentation entitled A Software Maintenance-Focused Process and Supporting Toolset for Academic Environments. This presentation will focus on the process component of this research. The toolset will receive more attention in a separate presentation for the tool demonstration track at ICSME. So, why do we need a new software engineering process? Software engineering processes have evolved to cope with the changes in how software is produced. Changes in workplace environment, organization culture, available tools, client availability, and involvement have all prompted corresponding changes in process. The software engineering classroom is an environment with many unique characteristics, including the relative importance of student learning and growth with respect to that of producing a product, and the varying levels of experience, availability, and motivation of student developers. These unique characteristics can be better supported by a process designed to account for them. A process for these environments that focuses on software maintenance is beneficial for a few reasons. First, maintaining an existing system instead of building a new system allows the experiential component of a software engineering course to be more scalable while affording time for a more conceptual course component. Second, software maintenance includes or acknowledges many of the activities used for new software development, but often with a smaller scope. And third, analyzing and modifying an existing code base imparts a better appreciation for writing maintainable code. So why do we need a new tool set? A tool set designed to enforce a particular process can help developers adhere to that process. And this is an important outcome for students in a software engineering course. And again, a tool set designed for the software engineering classroom can support its unique characteristics, including student growth, grading, and peer learning. This toolset has a particular focus on impact analysis, largely for two reasons. First, students often misuse Git, committing changes to files unrelated to their tasks. This often results in merge conflicts that are challenging to resolve, particularly when the class size is large. And second, novice developers who are unfamiliar with the project struggle to identify files that facilitate a given task. Here's a model for CoOp, the process and toolset described in this paper. Its early phases are scalable to account for the increasingly large set of desired outcomes in many software engineering or capstone courses. These desired outcomes may include both an understanding of conceptual content as well as a project-based experience. Let's get a quick overview of these phases. In the first phase, project setup, users obtain, install, and configure the project source code, tools, and resources. Class time should be devoted for this activity, and students with more experience in environment setup should be encouraged to help others. In the second phase, technology overview, an overview of the programming languages, frameworks, and tools used by the project should be presented. If conceptual content is important for the course, then instructors can include lectures and/or assignments on topics like version control, software configuration management, or unit testing during this phase. In the third phase, requirements analysis, the system's functional and non-functional requirements should be addressed. And depending on the desired outcomes for the course, this phase could be as simple as an overview of what the application does and why it was built the way it was. Or it could include lectures and assignments on requirements, design, and software architecture. After the initial three phases come the cycles. A co-op cycle is like a sprint in Scrum. Like sprints, cycles have a short fixed length, are intended to produce a new iteration of the system, and emphasize within-team communication. Unlike sprints, cycles do not include daily stand-up meetings, are not meant to produce a potentially shippable product, and emphasize impact analysis, review, and integration. Co-op roles include that of cyclers and mergers. Cyclers are responsible for running in-class and review meetings for their team. Mergers are responsible for merging the changes of individuals into a team branch. Each cycle consists of three sub-phases. In the first, cycle board and impact analysis, teams create and assign cycle tasks on the cycle board, which is like a product backlog in Scrum. Importantly, teams also collectively identify the corresponding files that will require modification to complete those tasks. Ideally, these activities take place during the first class meeting in each cycle. The second cycle phase is for implementation, and the third cycle phase is for an in-class code review and team branch merge. It's important for both activities to take place in class to foster the kind of communication necessary for these potentially tense activities. Ideally, the third cycle phase takes place in the last class meeting in each cycle. Here are a few screenshots of the CoOp toolset, which is implemented as a web application. The cycle view displays data including the types of tasks users worked on, when they worked on them, how much time they spent on them, and which roles they played in those tasks. Helping others and requesting help from others is recognized and encouraged by the system. At the top right, we can see the cycle board view, which is similar to a Kanban board. At the bottom right, we can see some task detail, accessible from the cycle board view, displaying the impact analysis detail for a given task. Importantly, CoOp includes constraints that prevent users from identifying a programming task as completed until the files modified in the identified repository commits match what was indicated in the task's impact analysis view. CoOp has been used in class sizes ranging from 13 to 81 students. In each instance, all teams worked on the same project. The instructor formed teams and assigned roles based on student surveys, and teams were updated between cycles as needed. The projects maintained using CoOp ranged from 6 to 12,000 lines of code, focused on Java-based web applications, and included frameworks and tools like Spring, Hibernate, and Apache Maven. The courses in which CoOp has been used include a Software Engineering 1 course taken by third-year undergraduate students, in which 8 weeks were devoted to the pre-cycle phases and 6 weeks were devoted to 3 cycles. Using CoOp allowed the course to cover both conceptual material and provide a meaningful project-based experience. In a Software Engineering 2 course taken by fourth-year undergraduate students who previously took Software Engineering 1, 2 weeks were devoted to the pre-cycle phases and 12 weeks were devoted to 6 cycles. Using CoOp allowed the course to provide a solid project focus and carry out significant maintenance work. Currently, CoOp is being used in a senior capstone course taken by fourth-year undergraduate students with no prior software engineering course. Here, 5 weeks are being devoted to the pre-cycle phases, with 8 weeks devoted to 4 cycles. If you're interested, the source code for the CoOp web application is available here on GitHub. Feel free to email me with any questions or comments. Thank you.